So finding empirical formula from moles is fairly straightforward, but unfortunately not terribly realistic. There's not really a way to directly measure moles in real life. So what we're going to look at here is actually some more real-world kind of problems for determining empirical and molecular formulas using mass and percent composition. You'll notice what we're going to end up doing here is kind of combining about the last 3 or 4 videos. So we're going to have to deal with converting mass to moles. We're going to have to deal with taking moles to empirical formula. We're going to have to deal with percent composition and what that means for our mass. So, starting from mass, like I just said, moles can be directly compared. They're always going to equal the same number of particles because 1 mole is always 6.02 times 10 to the 23rd, regardless of what kind of element we're looking at. Mass is pretty much never going to be directly comparable. You don't know how 1 gram of hydrogen is going to react with 1 gram of oxygen. So anytime you're starting from mass and you're trying to find empirical formula, you're going to have to convert to moles. For reference, this is actually true of most chemistry problems. If you're not in moles, you're going to want to get there. So let's work an example. A compound was analyzed and found to contain 13.5 grams of calcium, 10.8 grams of oxygen, and 0.675 grams of hydrogen. What is the empirical formula of this compound? So we looked in the last video at how to do it if we're starting with moles. We're not starting with moles, so getting to moles is our first step. You should be pretty familiar with it, but we'll work through. So we know we've got 13.5 grams calcium, 10.8 grams oxygen, 0.675 grams hydrogen. Okay? So we're going to have to convert each of them to moles. And we know that 1 mole of calcium weighs 40.08 grams. We need grams on bottom because we need units to cancel. And that's the molar mass, so it's in 1 mole. Same thing for oxygen. 1 mole in this case is going to be 15.999 grams. And then same thing for hydrogen. 1 mole is going to be 1.008 grams. Now, all of our numbers are on the bottom, so we're going to divide them. And that gives us 0.3368 moles of our calcium. It gives us 0.6750 moles of our oxygen, and it gives us 0.6696 moles of our hydrogen. You want to try and leave some extra decimal places at this point because the earlier you round, the more likely something is going to go weird in your final answer. So now at this point, it should look pretty much exactly like the problems we did in the last video. We've got everything in moles, so we know our next step is going to be divide by our lowest number. And our lowest number is going to be our moles of calcium, so we're going to divide everything by 0.3368, 0.3368, 0.3368, because we're trying to figure out the ratio of all our elements together. We're going to convert everything back to the lowest. So for calcium, we know a number divided by itself is 1. For our oxygen, we get 2.004, which is going to pretty much be 2. And for our hydrogen, we get 1.988, which we will 99, which will also round to 2. So our empirical formula for this is going to be CaO2H2. And that should actually make a lot of sense because if you think about what calcium hydroxide is going to be, calcium has a +2 charge and hydroxide has a -1. So if you have calcium hydroxide together, it should get you CaOH2. So that makes sense as an answer. All right, percent composition is only fractionally harder, and fractionally is frankly being generous. This one's going to be a little bit trickier because there's more elements involved and your numbers are going to get a little weird. This is probably more complicated than you're going to see on the worksheet or the test, but it's actually one of your more realistic problems. Percent composition is a good thing to start from because it's something we can actually measure in the lab. If you use something called a mass spectrometer, it breaks things apart into the elements and you can figure out what percent each of them makes up. percent composition you're going to do just like you're starting from mass. You just assume you're working with 100 grams. So if you're working with 100 grams, 1% equals 1 gram. So you just change all your percentages into grams. So we know we're going to have 57.14 grams of carbon. We're going to have 6.16 grams of hydrogen. We're going to have 9.52 grams of nitrogen, and we're going to have 27.18 grams of oxygen. And you don't have to assume 100 grams, but if you don't assume 100 grams, your math gets more complicated. Also remember, your total percentage has to add up to 100. So if it gives you 2 or 3 percentages and says the rest is something else, subtract what you've got from 100. All right, now exactly like the last problem, we've got to get some moles first because we can compare moles directly. So we're going to pull all our molar masses off the periodic table. So carbon is 12.011. Hydrogen's going to be 1.008. Nitrogen is going to be 14.007. I apologize if yours works out to 14.006. That's one of those ones that varies a bit from periodic table to periodic table. And then our oxygen is going to be 15.99 again. All right, so all our numbers are on bottom. We're going to divide them all. And just like in the last problem in the last video, once we've got everything into moles, what we need is our ratio compared to our lowest number of moles, which is clearly in this case nitrogen since it's less than 1. So we're going to divide everything by the number of moles of nitrogen we have, which is going to be 0.6797. Figure out what our ratios are. And you'll notice, unlike the last couple of problems where everything worked out to whole numbers once you rounded it, 6.999 will round to 7, 8.999 will round to 9, 1 is 1, but 2.5 is too far to be rounded. So we want to make everything in a whole number, so we're going to have to multiply everything by 2. So since we said this was 7 times 2, this is going to be 14 times 2, this is going to be 18 times 2, this is going to be 2, and then times 2, that's going to be 5. So our empirical formula, our lowest terms formula for this compound is going to be C14H18N2O5. All right, now the other thing it asks us to find is the molecular formula. So finding our molecular formula is also going to be just like in the previous video. We need to find the ratio of our empirical formula with our molar mass. So we know our molar mass of NutraSweet is 294.30 grams per mole. The total mass of our empirical formula you're going to find by adding up all of your elements together. We know how to do molar mass, so I'm just going to find that and put it down. So we add up C14H18N2O5. We find out that actually works out to 294.307 grams per mole. So if we divide that, we get basically 1. So in this case, our empirical formula and our molecular formula are actually exactly the same thing because our molar mass is equal to the mass of our empirical formula. Isn't that nice? All right, so now you've got 2 guided practice problems in your packet. Try those on your own. Come back, see if you're working it right. So this was a much more straightforward problem for finding empirical formula from percent composition because there's only 2 elements. So we should remember from the notes we just took that we needed to assume that we've got 100 grams of our substance just to make our math easier. So we've got 100 grams and we've got percentage, percent equals grams. So we know we've got 32.8 grams of chromium and we've got 67.2 grams of chlorine. And we know our next step is always going to be to get grams into moles. We always need moles if we don't have them. So our molar mass of chromium, we should have found on the periodic table, to be 51.996 grams per 1 mole. Our molar mass of chlorine is going to be 35.453 grams per mole. So let's do our division. So we got that we have 0.6308 moles of chromium. We've got 1.895 moles of chlorine. We know I have to divide by our lowest moles, which in this case is going to be our chromium, because we want our ratio to our least abundant element. So we know same number divided by itself is always 1. This is going to give us 3.004, which is pretty well 3. So our empirical formula for this chromium compound is going to be CrCl3, which means we've got chromium 3 chloride. All right, and our last problem. 300 grams of an organic sample which contains only carbon, hydrogen, and oxygen is analyzed and found to contain 145.946 grams of carbon, 24.3243 grams of hydrogen, and the rest is oxygen. What is the empirical formula for the compound? All right, so we know we've always got to get our grams to moles. So 145.946 grams of carbon, 24.3243 grams hydrogen. The rest is oxygen, so it's going to be 300 minus the other two, which gets us 129.7297 grams of oxygen, because you have to have 300 grams total. And as always, our next step is get to moles. So we'll use our molar masses. Okay, and this is our hydrogen, so it's going to be 1.008 grams, and this is our oxygen, so we're going to have 1 mole, 15.999 grams. If you haven't memorized carbon, hydrogen, and oxygen by the end of this class, then you're probably not paying enough attention, because we're going to use those a lot. They're really, really common. All right, so let's divide all these out, figure out how many moles we have. So we have our moles for each, and just like we've been doing this whole time, we have to go back and divide by our lowest, which in this case is 8.109 of our oxygen. So we can find the lowest possible ratio of our elements. All right, so we know this one's always got to be 1. This one works out to 2.98, and this one works out to 1.498. So this is basically 1.5, and we know 1.5 is too far to round, so we're going to multiply everything by 2. So if we multiply that times 2, we're going to get 3. We multiply this times 2, which is basically, so 2.98 rounds to 3, times 2 is going to be 6, and then 1 times 2 is going to be 2. Our empirical formula for this compound is going to be C3H6O2. That's our compound formula in its lowest terms. All right, so remember, when we're doing these problems, you always have to get mass to moles, because moles are directly comparable, mass is not. You always have to take percentages and assume you've got 100 grams. Like I said, you could assume you have some other number of grams, but it's going to make your math more complicated than it needs to be. So change percents to mass, change all masses to moles, and they're really pretty straightforward. You've got to then divide your number of moles by your lowest number, so you get your lowest terms ratio. All right, so go try the practice on your own, and ask questions if you need them.